Dynamic programming has to do with identifying subproblems, saving your solutions to those subproblems, and then refusing to repeat your work for the same subproblem. Mathematicians often spend hours trying to figure out how to save minutes. To be able to be done this way, a problem must have an optimal structure where it must contain overlapping subproblems. This is different than divide and conquer like in merge sort. This is because divide and conquer doesn't have overlapping subproblems. With dynamic programming, you are using some of the same analyses over and over because those subproblems overlap. An example of this is the Fibonacci sequence. This has an exponential runtime, 1.618 to the nth power, if you must recalculate the two previous steps at every step. But if you cache each step for the next problem as well, this becomes an algorithm with a linear runtime. In this algorithm, we store these solutions through memoization. This is a top-down approach. Tabulation is a bottom-up approach. In this bottom-up approach, we solve the smaller problem solutions to solve larger problems. For the Fibonacci sequence, these both run in linear time. Memoization is like saying, I need to drink tea, but I need my teapot. To find my teapot, I have to clean my room. But first, I need to procrastinate the cleaning. Tabulation is more like, I need to procrastinate some, then I'll clean my room, then I'll find my teapot, and then finally, I can get some tea. Next, we are going to talk about sequences. These often are called strings, though they do not mean what you would usually think of. Subsequences are a sequence of elements that are in the same order as the sequence, but not necessarily next to each other. One problem you often see is to find the longest common subsequence, LCS, of two sequences. The brute force solution, such as finding every subsequence of both and comparing them, will be an exponential problem. But using dynamic programming can get this down to an order of nm. If we have x equals x1, x2, x3 up to xm, and y equals the sequence y1, y2, y, etc. up to yn, and z is the subsequence z1 to zk, is the LCS of x and y, we can break this up into smaller subproblems through tabulation in dynamic programming. Let's say x and y are two strings that we want to find the LCS of. We start off with a matrix with every I and j values. This matrix is an n plus 1 by n plus 1 matrix. We already know the length of the LCS if either of those have no elements, so we can put zeros in the 0 row and 0 column. Now we will look at the first block we have not filled in. Since B does not equal C, we look left and up. Left and up are both zeros, so this block will be 2. It doesn't really matter whether the arrow points up or left, since they are the same, so we'll just pick one as a default. In this next comparison, C does equal C, so we look to the diagonal and add 1. Next, C and A don't match, so we look left and up again. The largest is to the left, so we point that way. When we compare C to C, even though there is a 1 to the left, we always look to the diagonal when they match and add 1. We continue this path until all the boxes are filled in. Now we look to the bottom right to see the length of the longest common subsequence. This box has a diagonal arrow. This means that this letter is in the LCS. This is the 6th letter in Y and the 4th letter in X. We can follow this back, finding each time there is a diagonal arrow and adding that to the LCS. We stop once we get to a 0. The other possible LCSs come in when we change which directions the arrows go when there was a tie. You can even change the start to a box with the same value as the bottom right. However, this would be extra unnecessary coding.